In the third equation, that would imply that, which one do you want to replace? You want to replace that with y cubed or this with x cubed? Doesn't matter, right? So I'll replace x cubed with y cubed. Oh, look how nice this is going to be. 2y cubed equals 16, which means y cubed is 8, which means y is 2, not plus or minus, right? Just 2? All right. Now what? Just plus because it's a cube, not a square. That means x is 2 because of this equation, right? Which implies that x is 2. Hey, this is promising. I've got 2, 2 so far, right? Can you give me what lambda would be in this case? Do we have an equation with lambda in it? Right here. Replace your y with 2. It would be, I'm telling you how I'm getting lambda here. 2e to the 4 over 3 times 2 squared, which is e to the 4 over 6. Whatever that is, who cares what it is. But there is a lambda, e to the 4 over 6. Everyone understand? All right. I'm only putting my marker away because it's starting to die a little bit. Am I done? What else do I need to look at? That was just saying that x wasn't 0. That's what happens, right? That's because y'all wanted to, well, no, the ruler wanted us to go and solve for lambda. So maybe we should check before we forget that, what happens if x is 0? What if x is 0? Are we going to run into any problems if x is 0? What's the problem we run into? Where? What equation? The first equation? If x is 0, the first equation would become y times e to the 0 because of this, right? Equals the right side, which is 0. Which, if you divide both sides by e to the 0, which is 1, or just turn that into a 1, this means y is 0. I don't see a contradiction yet. So that's OK? So if x is 0, y is 0. But the third equation is going to fall apart. Look at the third equation. In the third equation, what do you get? 0 cubed plus 0 cubed equals 16. Not happening. Got it? So that's not going to be the case. So I can't let x be 0. If x is 0, I'm never going to satisfy the last equation. With me? Because in order to satisfy the first equation, I have to let y be 0 also. So letting x be 0 forces y to be 0, and as soon as that's done, the third one's never true. What else do we need to look at here? What is that? Y, what? Oh, suppose y is 0 or not 0? OK, suppose y is not 0. I'll do it back up here. Suppose y is not 0. What are you going to go for lambda in the second one? Is that what you're going for? No? Is that what? Didn't we solve for lambda in the first one? Plugged it in here and then got all our stuff? What if we try and solve for lambda in that one? We're probably going to get the same thing. Suppose y is not equal to 0. Equation 2 becomes x e to the xy equals over 3y squared equals lambda. You following? Same sort of logic as before. OK, then from number 1, I can replace it's y e to the xy equals 3 times lambda, which is x e to the xy over 3y squared times x squared. Do y'all see this is exactly the same thing's going to happen? Our 3's are going to cancel. The e to the xy's are going to cancel. I bring my y squared over, x cubed. So I'm going to have y cubed equals x cubed again. Check. We've done that already, haven't we? Yeah, you can. You can just make sure you say, suppose y is not 0, and we're going to get the same result. Just make sure you state it, because I just don't want you to forget to check things, that's all. All right, what if y is 0? Suppose y is 0. Contradiction, right? We're going to not be able to get this one to be true. So that means we only have 1 point, right? What's going on then? Let's take a look at it. Something's going on here. First of all, this is, oh, well, I should erase some of that stuff, huh? I have the domain graphed separately here. That's your constraint equation. That's x cubed plus y cubed equals 16. Right there. That's what it looks like. If I plug just those points in to this, make one of these smaller. First of all, let's look at the domain on the ground. See the domain on the ground? If I plug just those points in, it's where this green thing intersects the surface. So I'm going to take that out. You see that? Got it? So just those points in, and it comes in, it spikes up, comes back down, goes, right? What does it look like is happening? Looks like we have a maximum, right? But then here, minimum, do we have one? That's asymptotically approaching what appears to be 0. But it's never getting there, which means you don't have a minimum. See, our restriction equation, I don't know if you notice this, our restriction equation, which is this right here, is not a closed curve. It goes in both directions forever. So we're not guaranteed to have a minimum or a maximum if the thing goes forever. So we should only have a max. It should only be that point right there. And do we know what it is? Well, I can tell you where it happens. It happens at f of 2, 2. Is that what it was? And what was the function's value at 2, 2? E to the 4th.
How would you know that's the max instead of the min?
Good question. How would you know that's the max, not the min? Great question. Just try and find a point that, give me a value, any value, that would satisfy that. Just give me anything. Make it simple. 2 and 2? Okay, so 2, 2 lives on that curve, right? Plug 2, 2 in there. Oh, hold on. Other than the one we just, yeah, sorry. How about, no, 1, 1 won't work. How about,
Isn't this Fermat's theorem?
what?
There's no
Oh.
There's no nice answers, or there's no whole number answers to.
Yeah, but I wasn't saying we had to use whole numbers. Yeah, I was thinking y'all would just like plug in 0 for one of them, right? And then just give me like cube root of 16. Like I thought that's what you would do. That's okay, though. 2, 2 works, but we already checked it. The point is this. You don't know if this is the max or min, right? So if you pick any other point on the curve, if this is a max, that's going to be smaller. If you pick any other point on the curve and the point when you plug it in is bigger, then that's a minimum. So all you have to do is check one other point. So what happens if I plug that in? What's f of 0 cube root of 16? That's e to the 0, isn't it? Which is 1. So 1 is definitely smaller than this, so this has got to be a maximum. Thank you for asking that question. I would have forgot to point that out. So it's a max. All right. Doing good, doing good.
How do we know what point is fixed?
Any point. Yeah, it has to satisfy the constraint, though. In my notes, I actually worked out the work for that one. Oh, look, I even did a point. Oh, see? To see if it's max, to find a point, satisfy 3 that yields a smaller value, plug in. See, I even use 0 cube root. I forgot I put that in there. Okay, let's look at this one. The reason why I'm going through all these, and of course I could let you do these on your own, is because each one of these, the algebra is just, a little bit different. And all right, I'm going to go through. I'm going to set this up a little bit quicker. Let me remind you, this is x to the negative 1 plus y to the negative 1. That this is x to the negative 2 plus y to the negative 2 equals 1. That's going to help me when it comes to derivatives. So my first equation is going to be what? Negative 1 over x squared. Is it all right if I do that? Yes? Equals lambda times, maybe I should put negative lambda. What? Negative 2 over x cubed. So how about I do this? Negative 2 lambda over x cubed. Second equation, negative 1 over y squared equals negative 2 lambda over y cubed. Pretty much identical, isn't it? And then the third is the constraint. Any ideas here? I can multiply, how do you mean? Like, do like a cross multiply, like this?
Or simply just multiplying the cube onto the left side and give you this.
Okay, yeah, I see what you're saying. So multiply here, both sides by x cubed. Multiply right here, both sides by y cubed. They're both negative, right, on both sides? So now if I multiply both sides by x cubed here, I have to promise x can't be 0, right? But do I need to worry about that at all? I don't even need to state it. Why? It's not even within the domain of the original function. So you're never even going to be able to talk about x being 0 or y being 0 to begin with. So I don't have to tell you, suppose x isn't 0, because then I would look like a fool, right? Because then I'm telling you to don't consider a point that's not even in the domain. So I'm just going to say here, from here, multiply both sides by x cubed. I get x equals 2 lambda. Over here, y equals 2 lambda. Hey, that's nice. That means x is y, right? X must be y. So suppose x is y. What can I do with that?
Plug it into the third equation.
Go into the third equation. The third equation would turn into 1 over y squared plus 1 over y squared, or you could say 1 over x squared plus 1 over x squared. Either way, right? Equals 1, which means 2 over y squared equals 1, which means y is equal to plus or minus the square root of 2. I'm just moving things around. Also, I multiply both sides by y squared here. Y can't be 0. I didn't need to state that. All right. I should be able to get 2 points from this, right? I know that x must be y, and this is what y has to be. So I can have, continuing still in here, I can have root 2. I could have negative root 2, negative root 2. I need to try and get lambdas for those. I think the lambdas are going to be pretty easy to get, right? If I solve both of those for lambda, just our x-coordinate divided by 2 or the y-coordinate divided by 2. But since the x and y are the same, this one will be root 2 over 2 and then negative root 2 over 2. So far, just two points that I need to consider, right? Any questions? Is there anything else I should do that's going to give me anything different? I don't see anything else, right? I mean, if I solved these both for lambda, I'd get x over 2 equals y over 2, which is still x equals y. I think we've covered it. Well, this one looked bad in the beginning, but it's turning out to not be that bad. We all right? Let's go for it. Let's see. What's f of root 2? 1 over root 2 plus 1 over root 2, which is 2 over root 2, right? Which is just, if you rationalize the denominator, is just root 2. And then the other one is just that, but negative, right? So it looks like we have a max and a min. This one has a really cool picture. That's why I wanted to show you this. May I erase? "20 minutes. Okay. This is the surface. Really kind of cool looking, right? X can't be 0, y can't be 0, right? So the entire x-axis and y-axis are gone in this picture. If I plug in the domain, that's your domain, okay? That's what it looks like. So it's really a cool domain. If I plug it into the curve, there it is on the ground. And now I'm going to plug in those points into the function. And you can't see, it's the black stuff. Boy, that's hard to see. Let me pull the function back a little bit. I don't know if you can tell. Can you tell? This curve right here is getting plugged in, and it's going right up here onto this piece. So what we figured out is that there were 2 points. Let's see. There's one of them. Okay, there they are. Check that out. There's one of them. There's the other one. We satisfied? You're going to have to get in here and get your hands dirty with the algebra. But now what we're going to do is we're going to extend this now. This is the beauty of Lagrange multipliers. It does not matter how many variables your function has. So if you have a function of 3 variables, subject to a constraint equation that contains 3 variables, you can find the maximum and minimum also. The equations are exactly the same. You set the gradients equal to each other, lambda, and then you satisfy that last one. So how many equations will we have? 4. Partial of f with respect to x equals lambda partial of g with respect to x. Partial of f with respect to y equals lambda partial g with respect to y. Partial of f with respect to z, which we didn't have before, equals lambda partial g with respect to z. And finally, the constraint equation. So those are the equations. Yes, y'all follow? Everyone said like in unison 4, so those are them, right? Okay, so what I'd like to do, is there anyone else who's already done the bonus question from last class? One person turned it in. Do you have it to turn in?
Yeah.
Yep, I'll take it right now. I'm going to do this problem. And then the problem's no longer offered for bonus.
Oh, wait. Oh, you said one bonus question.
It was the one, no, okay. The one with the rectangular box inside the ellipsoid. Remember that problem from the end of last class? Was it fun? I see it took you a little while. Well, the derivative was okay. Okay, so what I'm going to do is I'm going to go back to last class, which, if I can find, here it was. It was this problem. Do you remember that? We were trying to get the largest possible box inside this ellipsoid.